Suppose a shipment of batteries has arrived and must be tested to determine if the batteries are good or should be sent back. Suppose that the average life of the batteries in the shipment is claimed to be 120 hours. With a standard deviation of 12 hours and a sample size of 36, test the shipment with a level of significance of alpha equal to 0.05. The first thing to do is to set up a null and alternative hypotheses. The battery's average life is claimed to be 120, so I'll assume that the batteries are at least that. And then the alternative is that the batteries are less than an average of 120 hours. In running a standard type 1 analysis test, my second step would be to create the sampling distribution. The center of the sampling distribution is 120. And if I calculate the standard error, by the way, we're using the population standard deviation of 12. The variation of the life of the batteries is known, so they would have some approximation of sigma that would be very close to sigma, so close that we can consider it sigma, and sometimes that's called a planning value. So we can have, for a sample size 36, we have standard error equal to 2. Now this would be a lower tail test, and alpha is 0.05, and my critical value is 1.645. And step 3 is my rejection rule. I'm going to reject H sub 0 if Z, the test statistic, is less than or equal to negative 1.645. Now in a type 1 analysis, I would calculate the test statistic at whatever sample average that I had, and then compare that test statistic value to the critical value of the negative 1.645 and determine whether I would reject the null hypothesis or do not reject. Now, this is a situation where I want to make a decision. If I reject the null hypothesis based on this test, then I would send the batteries back and be confident that there was a problem. However, if the test concludes with do not reject, that's at this point showing that there's not enough proof that the null is wrong. But also we've seen that that's not enough proof that the null is correct necessarily. So a do not reject is really inconclusive. If I let do not reject basically mean accept, because I have to make a decision in this situation, then I'm running the risk of type 2 error, of accepting a shipment that turns out the null hypothesis is false, the shipment is bad. To try to analyze the probability of type 2 error, I'm going to change the procedure here a little bit in the hypothesis test. And instead of running the test using a critical value, I'm actually going to run the test using a particular sample average value. And what I'm going to do, you know that the Z value here, the test statistic, is going to be whatever sample average I have, subtract the average, claimed average of 120, divided by the standard error. So what I'm going to do is replace the Z value here, the test statistic value, with how I will calculate it in step 4. It's whatever sample average I would have, subtract the 120 divided by 2. And now I'm going to solve this for the x bar. So I'm going to multiply both sides by 2. So I got x bar subtract 120 is less than or equal to negative 3.29. and then x bar, adding the 120 to both sides, I'd have x bar is less than or equal to 116.71. So my new rejection rule is to reject h sub 0 if x bar is less than or equal to 116.71. Now notice up here at the decision line in our problem, that has a z-score or critical value of negative 1.645. It's also the same place where the sample average is 116.71. So all I've done really is to change the rejection rule so that instead of taking a test statistic from some sample average and comparing it to the critical value, I'm going to take the sample average itself and compare it to 116.71. And I'm going to reject the null hypothesis if my sample average is less than 116.71, which is really equivalent to comparing its test statistic or z-score to the critical value. So I'm running the same test. I've just changed what values I'm comparing to determine where the sample average is. Is it to the left of that decision line, which means I'd reject, or is it to the right, which means I do not reject? But in this case, I'm going to go ahead, because I'm analyzing type 2 error, I'm going to go ahead and accept h sub 0 then if my sample average x bar is greater than 116.71, and create what is called a decision statement or a decision rule. Now, I'm going to try to analyze this problem for type 2 error. And as you know, type 2 error is accepting the null, and it turns out that the null is wrong. So I'm going to investigate the probability of making a type 2 error based on different values of the population mean. For example, suppose that the actual population mean is 112 hours. Now, if I accept the null hypothesis as being true, that the battery average life is at least 120, and it turns out that the real average life is 112 hours, then I've made a type 2 error. So the question here is, if the actual population average is 112, what is the probability of making a type 2 error? So if mu is equal to 112, then what is beta? Beta is the probability of making a type 2 error. How can I calculate beta? Well, let's look at the decision statement. And I'm going to accept the null hypothesis if the sample average is greater than 116.71. If the real population average is 112, in other words, the sampling distribution is really centered at 112, then what is the probability that the sample average that I get is greater than 116.71? That probability is the probability of making a type 2 error. And that's determined by finding the area under the density function, the sampling distribution, from 116.71 on. Now, how do we do that? Well, we have to find a z-score for the 116.71. So we'll go out here to the left a little bit. 116.71 1.71, subtract 112, and divide by the standard error, and I get a z-score of 2.36. Now looking up 2.36, in the standard normal table, I get 0.9909, and I would have to subtract that from 1 to get beta, and beta is going to be 0.0091. So what I've calculated here is the probability that I would accept the null hypothesis in a situation where the population average life of the batteries is as bad as 112. There is about a 1% chance that I would accept that shipment. So the type 2 probability of making a type 2 error is pretty small if the average life of the batteries is actually 112. Now I want to analyze the situation where the average life of the batteries turns out to be 115. So if mu is 115, then what is the probability of making a type 2 error? Okay, in this situation, I'm going to try to draw this so we can compare it to what we've already done. Again, I have my 116.71. If the real population average is 115, then I'm going to have a little bit more probability of making the type 2 error. I'm going to calculate the z-score here. The real average is 115, the real population average, and that gives me a z-value of 0.855, and I would look up the 0.86 in the table and find that the probability from the table there is 0.8051, and then therefore my probability for beta is 0.1949, or 19.49%. Okay, as the real population average changes from 112 to 115, the probability that I will accept the null hypothesis under those conditions is going to be greater. The closer and closer the population average gets to 120, the harder and harder it will be to reject it based on a sample of size 36.